Well, thank you. Well, I hope you hear me. Ben suggested at some point we should make a leaderboard of how many talks people have had or given at Friday talks. Um, Apparently, I'm not so bad on this leaderboard, but I think it's not true because I rarely talked about some content. And so maybe that's the first time I will talk about some research content. Um, and to be honest, it's not even research content which I'm standardly like looking at it. It was a project which I pursued when I was in Philadelphia visiting these two nice persons, um, and actually several persons more in this group who do computational game theory. And within this, within the stay, we specifically Natalie and we developed what I'm going to present today. So imagine you're a penguin farmer. Well, penguins, because I always need to have some penguins in my talk. And why a farmer? Because what I want to look at is some simple game and some simple game mechanics. Okay, the game works as follows. The penguin farmer has some chicken, obviously, and this penguin farmer can take decisions, for instance, whether to give a drug or not give a drug, but this costs under certain circumstances. And then on the other hand, that's what I marked here in green. There is some kind of examiner person, essentially like a regulating agency, for instance, coming from outside, maybe the state or something else, looking on how well you treat your chicken. Okay, and I'm gonna make up some kind of numbers later on and how the two agents behave and what their incentives are. Don't take this too serious, please. Um, what's the setup? The setup is what is called a simple Stackelberg game, or it's actually going to be extended afterwards. So in a Stackelberg game, you have at least two persons or two agents. One is called leader here in green, and one is called follower in blue. Both of those agents have different actions which they can take. For instance, the leader can take the actions A, B, C, and the follower can take the actions I and double I. Okay. How this game is set up is essentially I give utilities for different action combinations based on what leader and follower do. Okay. So this is summarized in the upper table for the leader in terms of the utilities for the leader, and in the lower one for the follower. And why do I say leader follower all the time? It's because of a certain protocol which is underlying this game setup. Okay, so the protocol works as follows: you have a leader. This leader is allowed to choose a probability distribution over its actions. So you can imagine pretty much like choosing a coin, which action to take. Well, if it's ABC, maybe it's not a coin, or a three-sided coin at least. And then the follower responds to this action, so actually like to this randomized action in the best possible way. That means it's maximizing the expected utility under the distribution of this action. Okay. Now, there's not going to be like when you maybe have heard some game theory things, there's usually like an interaction between both the players. That's what's happening then in Nash equilibria. In this case here for a Stackelberg game, it's pretty much like a sequential thing. Okay, one person committing, the leader committing to a certain probabilistic action in this case, and the follower just responding to it. And now the leader obtains the expected utility with respect to the best response which the follower has given, and the leader's idea is pretty much the incentive is to maximize its expected utility. Okay. I use, just as notation, I use the big V on the small v's for the follower, and I use the big U and the small u's for the leader. Okay. So far, so good. Well, we extend this game a little bit, and we do not only include a single follower, but essentially we include a set of farmers, a set of followers. And in this case, it's just simply extended. So the leader chooses a probabilistic action again, and then all of the followers best respond with respect to their own utility function, which might be different. And the leader obtains then the summed up expected utility for the different sub-games which are defining the entire game in total. Okay. Cool. Now, what's the twist of our paper? The twist of our paper is what we call ambiguous commitments. This game, which I've shown you before, has been studied in different setups already. There exist certain solution strategies, computational strategies as well to compute the best possible commitment of the leader, and obviously as well for the followers how to respond. Ambiguous commitment is the following idea. We say, instead that the leader is choosing a probability distribution, it chooses a set of probability distributions. So it's pretty much like saying the leader is not committing to a single coin which is going to flip and then take its action. It's actually committing to a bag of coins, and one of the coins is going to be taken, going to be flipped, and this action is going to be taken. The followers, however, they only know this bag of coins. Okay, they don't have any further information. They don't know exactly the specific action which is going to be taken. And for that reason, we model the followers as best responder, maximum best responders. So they are afraid of that they choose, like a bad coin is going to be chosen from this bag, and then they best respond to what they expect to be the worst case for them. Okay. We as well include this worst case situation for the leader. So the leader as well, the leader doesn't know which coin is going to be picked from this bag. So as well, the leader is going to expect the worst case among its options, which it commits to the set, to the bag of options here. Okay. Well, why is this interesting? Well, it turns out first, it's not interesting at all, because if there's only a single follower, we have this informally written statement that it does not matter. It doesn't matter whether you can have access to a bag of coins or whether you can only have coins, okay? So people who have access to a bag of coins and they face only a single follower. So for instance, this regulation agency is only looking at a single farmer. It doesn't matter what to do. It can just pick a single coin, can just commit to a single distribution. But what about the same setup with multiple followers? And here it gets a bit interesting, okay? And I've brought you this simple example to illustrate what's happening. Let's imagine that the leader has the following actions. It can control farm A and B. It can control farm A, it can control farm B, and it can control none of the farms, okay? The farmers, they can give the drug or not give the drug to the chicken, okay? Now, it's a bit weird in the setup because the followers want to maximize. So the followers want to maximize this reward number and the leader wants to minimize, okay? Why is that a bit weird? Because that's just saying that the leader wants the followers to be bad, which is hopefully not always the idea of a regulator, okay? But in this case, it should just illustrate what's happening here. Because the two players have opposing incentives, that's a zero-sum game. They essentially do exactly the opposite of the other person. Okay. Now, looking at this game, looking at the numbers, you're going to observe that for the farmer A, for instance, it does not matter whether the regulator goes to the farmer B. Okay. It only matters when it goes to farmer A. Okay. As well, what you're going to notice is if the leader can commit to the A-B control action, it can guarantee that the farmers, both of them, are going to give the drug. Okay? The followers want to maximize, the leaders want to minimize. The leader commits to the full A-B strategy. That way, the farmer A will best responds with giving the drug, and the same as well for B. It's not the case if it just goes to A or B. Okay. Now, in this setup, it looks like, well, there's a precise strategy. There's actually like a pure strategy to be taken. So we have to make this game a bit harder to show where ambiguity helps. And what we do is we introduce a resource constraint, essentially. And the resource constraint is the leader can go, so the regulator or leader can only go to one farm. It's gonna go to one farm, but it can only go to one farm. Now, the utility tables look a bit different, yeah, or essentially they're cut short. If you now do the calculations, you can show that whenever you take any precise probability, any precise commitment, so probability distributions over going to farm A or B will lead to a certain pattern where the farmers respond by sometimes not giving the drug. One of the farmers is not going to give the drug. And here the interesting thing is whenever the leader commits to an ambiguous set, so it says, like, I don't know myself which coin I'm going to take and to which A, like whether I go to farm A or B, it's going to be a third party deciding that. Then because it's the worst case, because the farmer cannot calculate or don't know exactly what's going to happen, they take the worst case and they're going to give the drug in both cases. So we can, like, what essentially is happening here is we can evocate a response pattern which is unreachable by any precise commitment. Okay. What I mean by a response pattern is that both the farmers give the drug. We can make this formal and give this theorem which says that there's more than the simple game, that there's a set of such games where where this ambiguous commitment helps a lot. And at that point, I'm already going to conclude, even though there's some even nicer results afterwards, which take a bit more time to explain. I want just to say, because we're in a computer science department here as well, we have some computational results, which essentially gives us a clue of, can we calculate such strategies, such ambiguous commitment strategies? And we do give an algorithm for that, at least as long as the leader has not too many options in its action, because we show that its NP-hards are pretty complicated to get to those commitments whenever the actions can grow. With this, I hope regulation has some new idea what to do, or maybe not. Well, at the end, it's a model. And what I want you to take away is this nice quote from Winston Churchill, or maybe someone else, is ambiguous commitments help to raise the Stackelberg value in multiple follower games. Thank you.